In this video, we'll talk about the role of auxin in phototropism and in gravitropism. In phototropism, when light, directional light coming from one direction, hits the tip of a shoot, that causes auxin to move from the side facing the light to the side facing away from the light. Here's light. And then you get auxin moving to one side. Why do you get auxin moving to one side? Because if this was a cell within the shoot tip, the auxin efflux proteins would all move to the side opposite the light, and auxin exits cells only through these auxin efflux sites, remember? And then you would end up with more auxin on the side of the shoot facing away from the light. Now, the total quantity of auxin made isn't going to change, and so whatever is added to this side of the shoot has to be subtracted from this side of the shoot. Auxin leads to elongation in this situation, so that you get this end elongating faster, this end elongating shorter, and that's what leads to the bending. This being a small space, this being a large space. There's the source of your bending. The cells on this side are longer than the cells on this side. Auxin has been moved across to accomplish this, and auxin has been subtracted from this side to make these cells elongate ever more slowly. Why do cells elongate more quickly when auxin arrives? Well, auxin comes into a cell within the elongation zone and activates the proton pump. So auxin enters the cell and it cranks up the proton pump. And that means more protons leave the cell. If more protons leave the cell, then that's going to raise the pH in the cell and decrease the pH outside of the cell. In addition, this is going to hyperpolarize the membrane. Hyperpolarization of membranes of the elongation zone, not every cell, mind you, but within the elongation zone, leads to the opening of voltage-gated potassium channels and activation of sucrose, proton, so sugar or sucrose, and proton into the cell through this sucrose-proton cotransporter. Now, this is stuff, and this is stuff. They're solute, and so that causes a decrease in the osmotic potential of the cell. That decrease in the osmotic potential of the cell draws in water, which leads to an increase in the pressure potential of the cell. Okay, so now you got a cell that's under more pressure. That cell is being held in place by a series of belts, cellulose microfibril belts. They are hooked together by quick links, these hemicellulose fibers that hold together the belts. Because of the decrease in pH caused by proton pump activation, which was caused by auxin, you have expansin activation. So expansins are proteins that only work at low pH. They're already out there waiting for this signal to occur, the low pH signal. And when it does, they cause the breaking of these quick links. And now the cell is capable of changing size. It elongates. It elongates because those three belts are still there. But now the quick links aren't holding those belts together, so the cell can become much longer, and the belts are just now further apart. That's how come you get elongation over here. And it looks something like this if we draw the kinetics of it. The more auxin you have in the chute, the greater the amount of elongation you get. This is the process that I've just described is called acid growth. and acid growth is what I have drawn. And, there's a maximum amount of growth that's possible. And here's the percent elongation, and here's the auxin concentration leading to that percent elongation. However, auxin at high quantities leads to a second response, and that is the production of ethylene. And ethylene blocks elongation. Ethylene blocks elongation and by mechanisms we don't really know, but what this means is the overall elongation effect of auxin starts to decrease until get enough ethylene and you don't get any elongation at all. So this is all the ethylene effect over here. Okay, so auxin is causing both the elongation, and then even though this elongation acid growth factor is still active, ethylene overcomes that signal to elongate, and it stops elongation. Interestingly, this ethylene and acid growth relationship is also true in the roots, but roots are much more sensitive to auxin, so their acid growth occurs at very low auxin concentrations, and their ethylene cancellation of elongation happens at very low concentrations, but for exactly the same reasons. Okay, so here would be the root response to auxin with respect to elongation, and the shoot. This is the root side of the graph. This is the shoot side of the graph. There's another tropism that you should keep track of, and that's gravitropism. So if you turn a shoot over on its side and it had some stable equal concentration, so here's the up and down shoot, here's the up and down, here's the elongation zones in the root. Over here, this equals this, and this equals this. Now, the concentration of auxin is going to be higher in the shoot than it is in the root. That's good, because if you remember what the elongation factor was, better be higher in the shoot than it is in the root. Otherwise, you're not going to get any elongation in the shoot or any elongation in the root. Okay, so get rid of that. What happens if I turn my plant on its side? Turn my plant on the side. All the auxin is moved because the efflux carriers are moved, so that the auxin ends up facing downward, facing towards the center of the earth. That means the auxin concentration facing up is diminished. There's the same amount of auxin being produced, same amount of auxin traveling through, same amount of auxin being redistributed here. So total quantity of auxin in these two is going to equal this total amount of auxin in these two. Total amount of auxin in the shoot isn't going to change. You're going to have the same amount in those two as you do in these two. However, these are not equal. This has got a greater amount of auxin. This has got a lesser amount of auxin. This is a greater amount of auxin. This is a reduced amount of auxin. But because of where these things lie along the kinetics curve, here's the shoot curve, here's the root curve, here's the root curve, here's the shoot curve. Because the concentrations that you're going to find of auxin in the shoot are going to fall within this range, any increase in auxin leads to an increase in elongation. So the shoot ends up bending up. Any increase in the amount of auxin in the root, however, leads to a decrease in elongation. See, as you increase auxin, you decrease elongation. That's why this elongates less than this. If this was where they started, Now they're here and here. You'll see that the one with less auxin elongates faster. The one with more auxin elongates more slowly, and you end up with the root bending down as a result.